My name is Kathleen Smith. I'm an associate faculty member at the Bowen Center, and I want to welcome you to what month is it? Our January professional lecture. And tonight, just as a quick reminder before I introduce our speaker, that there will be some space for discussion throughout. Dr. Brailsford will let you know when she's taking questions and comments. And we ask that you use the raise hand function on Zoom, and I will call on you and you can share your thinking at that time. So it's a privilege to introduce our speaker tonight, Dr. Krista Brailsford. She is a research scientist in the Geospatial Science and Human Security Division at Oak Ridge National Laboratory. Her research uses data science tools from economics, geography, network science, and spatial statistics to describe the coevolutionary processes between human systems and the built and natural environment. These analyses have been particularly focused on urban contexts, exploring themes of urban water management, infrastructure provisioning and resilience, and human behavioral responses to surprising events. And Dr. Brailsford was previously the Leanne Russell Fellow at Oak Ridge National Laboratory and a postdoctoral fellow at the Santa Fe Institute. She obtained her PhD from the School of Sustainability at Arizona State University for research on the determinants of residential water demand. Dr. Brailsford is currently leading efforts to use novel data sources, such as digital trace data, to generate real-time measures of community structure and behavior change, and to describe the drivers and consequences of those outcomes from a national security perspective. And I'm looking forward to her explaining everything I just read. And she was recommended to us as a speaker from our faculty member, Jake Morrill. So thanks, fellow Tennessean. So thanks to Jake for recommending her this evening. So Dr. Brailsford, if you're ready, I will turn it over to you.
Great, thanks so much. And thanks so much for having me. And thanks everyone for being here tonight. Yeah, I'm excited to talk to you all. I'm going to see if I can walk and chew gum and share my screen correctly. Okay, can you folks see like the big version of my slides? Okay, doing well here. I think I can see you all. So again, my name is Krista Brailsford. I was a research scientist at Oak Ridge National Laboratory, and I was a Tennessean, but now just this month, I've moved to Los Alamos National Laboratory in New Mexico. Yes, so, but I've always believed that the purpose of science is to do good in the world. And I really feel extraordinarily lucky that I get to spend really a good portion of my days trying to understand, prevent, and mitigate what I see as the biggest risks to our global society. For a long time, that's been climate change, and more recently, that's been COVID-19. I'm a data scientist with a lot of experience in how cities function, though. So what good is that for disease or climate change? Cities are where a lot of the people are, and so they're also where a lot of our opportunities for influence happen. Through this talk, I've got sort of 3 chapters, more or less. And for me, it's much more interesting to give a talk if there's a little bit of feedbacks in the middle. So when I get to these stopping points in between the different chapters of the talk, I would love it if you would raise your hands or pop questions in the chat and moderate that however it works here, so that I can sort of get a sense of what you all are thinking. Thank you. All right. So human processes are the single largest driver of uncertainty in the future of the Earth system. The International Panel on Climate Change, the IPCC, if folks have heard of that, it's a behemoth of an intellectual product. Scientists from around the world with representatives from 195 nations. It's a consensus document, which means that every statement on every page has been agreed to by both Saudi Arabia and the small island nation of Tuvalu, and every country in between. So this figure is from the IPCC, and it shows projected temperature change and uncertainties across some scenarios of future greenhouse gas emissions. One thing that I think is really obvious from this graph that you can see is that uncertainty across the scenarios is far larger than uncertainty within any one of the scenarios. And this fact is the case across geographic scales. Our biggest uncertainties about coastal wetland loss is, are we going to protect wetlands or not? Our biggest uncertainty in wildfire risk to humans is how we choose to treat the urban-wildland interface. Our biggest uncertainty in urban flood hazards is how we manage water through infrastructure, land cover, and coastal hardening. But most Earth system research isn't designed to estimate human-scale consequences. Deborah Cohen argues that the global models we use to capture planetary scale effects of greenhouse gas emissions don't have the capacity to predict impacts at decision relevant scales. She makes a compelling historical case that this choice was not inevitable, and it's not the only possible strategy for doing climate science research. Climate research at the scale of decisions and impacts is possible. And I think this perspective is really important because we know that the consequences of climate hazards spread far beyond their direct geographic impact via things like via our economy and infrastructural connections. So Sugar, Werner, and Sato estimate that the share of damages, which are secondary impacts from large hurricanes and cyclones, these are damages triggered by production and supply chain disruptions rippling across global economic networks. For the largest storms, these distributed damages can be 3 times larger than the direct damages. And in order to consider and assess risks in their own domain from climate hazards, I think people need information tailored to their problems and at decision-relevant scales. So Simpson et al. Described their framework for addressing cross-system and cross-sector complex climate risks, building on different ways of characterizing vulnerabilities, hazards, and exposure. So this body of literature is arguing that climate research as a tool for addressing the climate crisis really needs to center people. And this isn't a talk that's all doom and gloom. There are good things coming too. So every opportunity to address the climate crisis goes through human systems. This figure is a summary of mitigation opportunities, again, that's been published by the IPCC. This is a summary and it's reductive because it separates things out by sector when we know that all these sectors interact, but it's comprehensive and it's pretty darn unassailable. One important point that I want you to note here is that anything in blue are things that reduces emissions and saves us money under current technology and with current prices. So all we have to do is do it, and we'll make a lot of progress. So there are big opportunities for emissions reductions in the energy supply sector. There are some opportunities for emissions reductions in how we manage land, water, and food. There's lots of opportunities in the buildings and infrastructure sector. And there are opportunities for climate action in the context of institutions and social processes. And when you add all of these things up, we really can get a long way towards addressing the worst consequences of the climate crisis with technology that we have right now under costs that really are feasible. We have made a good start and we can do better. And all of our opportunity to address these problems goes through human systems. And if the COVID-19 crisis that we just sort of lived through taught us anything, it's that human innovation and a whole of society response can indeed transform our lives in a timescale of days. So back in 2020, each of us participated in the largest collective behavioral change the world has ever seen. Isn't that an incredible thing to be part of? So this is a figure showing changes in median travel distance in United States counties in the spring and summer of 2020. You can see in early March when COVID arrived. This isn't when the virus turned up in the United States, but it's when it's turned up. It is when it turned up in our collective consciousness. And within a week, half of Americans lived in a county where typical travel distance had fallen by 95%. And 95% of Americans lived in a county where travel distance had fallen by at least half. We have never in the world seen such dramatic behavior change, and it was for our collective good. We can do it. Of course, we know how COVID went. Across all geographic scales, from cities, states, and nations, we've all lived through multiple waves of infections. These particular figures were drawn at the height of the Omicron wave in December, in that sort of January, December 2021 phase. So basically everywhere now has lived through another couple of major rise and falls in cases, right? This pattern of waves is significant enough and persistent enough that almost everybody now talks about COVID-19 waves. And in some ways, it's not really controversial anymore to think about them as driven by behavior, in part. But we still talk about disease spread using an epidemiological model called an SIR model, a segmented population model. And these mathematical models can only produce a single wave in infection if you use the sort of baseline strategy. And even published papers don't generally focus on behavior as a part of the disease system. So in May 2021, a scientist named Nicola Pera published a literature review where he read 390 papers and he categorized them. All of them focused on non-pharmaceutical interventions towards addressing COVID-19. A lot of them discussed measurement and data issues, which is a big problem. About 40 of these papers aimed to quantify the effects of non-pharmaceutical interventions. But only one of those almost 400 papers looked at the role of case spread in driving behavior change. And there's one paper from back in 2008, which proposed a model looking at interactions between case spread and behavior change. Josh Epstein noted that if you add a fear response to these traditional epidemiological models called SIR models, then you can produce waves and cases based on a fairly small extension to this standard model. But for the most part, our scientific focus hasn't been trying to couple social and social and epidemiological systems. But I think that endogenous analysis of anthropogenic processes is critical for addressing the world's largest problems. Every mechanism we have for intervention goes through human processes. If it's newly built infrastructure, new policies, different incentives, different punishments aiming to get people to change their behavior, it's all mediated by social processes. And so cities actually make a really good laboratory for studying interdependencies between human processes and other systems that build a natural environment, because cities act as concentrators for interactions across these different kinds of systems. So you can start to think about urban science questions from a couple of different lenses. One lens uses the idea of social scale. Just like a tree is distinct from a forest, the processes, drivers, and interactions among people mean that individual choices, community scale processes, and institutions each have unique mechanisms for influencing their broader context. And then, as with geophysical processes, important process interactions in urban contexts differ across spatial scales, from neighborhoods through neighborhoods, cities, regions, nations, up to the entire planet. You can think about sectors: the energy sector, water sector, land, health. All of these different sectors connect people and resources across urban or regional contexts, from smaller to larger scales, and through infrastructure networks and management institutions. Urban systems are embedded within larger environmental systems, and so it's valid. They're vulnerable to changing hazards, from geophysical and ecological, which sort of, when you start to look at it from this lens, scientists often come up with questions about resilience and adaptation. And this provides one lens through which we can understand differential outcomes and interactions across sectors and scales. And then finally, this outer circle here highlights the ways that we create knowledge about urban and human systems. So different ways of knowing are possible, and each uniquely contributes to our ability to understand and make sense of complex urban environments. Observation, theory, modeling, empirics, and collaborative knowledge co-production each have distinct contributions to how we can understand a system. So to illustrate that a little bit more, the next set of pictures are a series of cartoons that I drew highlighting what we view as the unique contributions of a bunch of different disciplines for our understanding of cities. So urban economists, it's not wildly wrong to characterize economists as thinking of cities as a well-mixed bag of interesting people, more or less abstracting away their spatial heterogeneity in order to focus on the role of behavior, choices, and policies. Similarly, it's reasonable to consider urban planning as a discipline that views urban locations as a function of interactions, and then more or less abstracts away important heterogeneities in behavior in order to focus on spatial properties. Engineers, on the other hand, focused on the role of infrastructure in defining urban form and function, with the view that above all else, urban infrastructure defines how people move, interact, and receive services. And then finally, the space of urban complexity sciences. This is a joke towards physicists who want to summarize everything as a sphere. has been trying to look for fundamental generalizable properties across all of the urban sectors, abstracting away many features of each of these disciplinary domains. And so these disciplines really have each made important contributions towards understanding cities for different purposes and with different scientific objectives. But a common theme among each of them is that they treat interpersonal interactions as the most fundamental and defining characteristics of cities. This makes sense. Cities exist to enable the circulation of people, goods, and ideas. And then we argue that because this observation has been made by researchers from very different perspectives and with very different objectives, it's more likely to be something that's fundamental. But of course, up until recently, actually measuring those interactions at scale has been deeply, deeply challenging. We've looked for the signatures of interactions in a bunch of different ways, but each of them really has been at a pretty coarse scale that misses a lot of important heterogeneities in people's experiences and outcomes. So what are the signatures of those interactions across scales and geographies? This is a good point for questions. I'm gonna sort of explain how these three little chapters in the talk go. But if you've got questions so far, I am open to hearing them. Okay. So what I'm going to do in this talk is run through three different projects thinking across social scales. In one example, I'll use diphtheria cases in the early 1900s to look at the temporal dynamics of urban disease transmission over the period when a commercially viable vaccine was introduced. And then I'll use COVID-19 to look at present day interactions between the social process of transmission mitigation and the biological process of epidemic spread. And then finally, I'll switch from diseases to urban infrastructure. And at the city scale, I'll show some strategies for measuring and understanding heterogeneity and inequality in urban infrastructure specifically. Okay. So there exists a theory called urban scaling theory. And one of the purposes of this little chapter is to talk about how the scaling theory is both predictive and it can be broken. So diphtheria was a major cause of death in the 19th century. And around the tail end of the 19th century, some antitoxin treatments were invented and their use became widespread. In January 1922, there was a major diphtheria outbreak in Nome, Alaska. Teams of dogs, I grew up in Alaska, so I'm always fond of this story, but dog sled teams were the final leg in the relay to get this antitoxin from Seattle all the way up to Nome. And so this is commemorated now in the Alaskan Iditarod, which is a 1,000-mile race from Anchorage to Nome. In this particular example, I'm using records of urban disease cases to explore a fundamental theory about how cities serve as social reactors, where they pass on both new ideas and also disease. So the fundamental idea of urban scaling theory is very simple. For every doubling of a city's population, a broad suite of aggregate socioeconomic outcomes more than double. They double and add about an extra 15%. And so in this figure, we can see that a bunch of socioeconomic characteristics are well described by this mathematical function. In this theory, urban infrastructure scales sublinearly, which means that you need less infrastructure than you'd expect as an urban population doubles. And socioeconomic output, things like wealth, patents, innovation, crime, those scale superlinearly. They double and add a little bit more. Now, these scaling results show up all the way around the world. You can see it in South Africa and Brazil and Europe. And to the extent that we have the data, they also show up throughout history. So the theory underlying scaling effects is interaction-based. Interactions are what generate new ideas. They generate anger, which is one of the inputs for crime. And interactions also are one of the primary mechanisms through which infectious diseases are spread, right? So cities have long been recognized as hotbeds of wealth, crime, and disease. That particular idea isn't new. In the story about Dick Whittington and his cat from 400 years ago, they thought that London streets were paved with gold. So this idea of urban scaling theory is in some ways just scientists finally recognizing the empirical reality in what people have intuitively understood for hundreds of years. But within urban scaling research, there hasn't been as much discussion about how scaling laws show up in a disease context, in part because before COVID, this was hard to measure. So one of the things I did was I started looking for data sets of historically important diseases that we now have vaccinations for, because vaccinations should break the transmission dynamics that cause the urban scaling effect. People still interact with each other, but those interactions, when we're all vaccinated and the vaccines work, don't lead to as much disease. So I found a data set on diphtheria in the United States between 1916 and 1948 and decided to test how well this particular theory turns up. So this is a time series of how many diphtheria cases there were in the United States in this period. In 1923 was when the useful part of the vaccine was invented. In 1926, we invented a way to keep it shelf stable. By the 1930s, the diphtheria vaccine was in widespread use, and by the 40s, it was in routine use. So this is a graph where each dot is a United States city. The x-axis is the log of that city's population in some year. So the population, 10 to the 5 is a population of 10,000. And the x-axis and the y-axis is the log of the number of diphtheria cases in that same city. So here, the dashed dot light blue line shows the naive expectation that the number of diphtheria cases increases in direct proportion to the city's population. So that would be saying that you're no more likely to catch diphtheria if you live in a small city as compared to a large city. The dark blue line shows the theoretical expectation that you're more likely to catch diphtheria if you live in a large city compared to a small city. And then the black line and the gray area around it are the best estimate and confidence intervals from the data that I have in any particular year. Now, before the invention of a vaccine, the data is very consistent with the theoretical expectation. It might not perfectly match the 7/6 estimate, but it's clearly superlinear. And then in the 1920s, we invented a commercially viable, shelf-stable vaccine. Diphtheria vaccination became widespread finally by the 1930s, and watch how this slope just falls from the superlinear rate down to the naive expectation in just a few years. And then by the 1940s, you can see total disease cases falling all the way until there were 0 cases in the United States in 1948. So that's a fun video, but in some ways it's easier to look at when it's not moving anymore. So what this figure shows is the slope of that line, where 7/6 is the theoretical estimate. You're more likely to catch diphtheria if you live in a big city, and 1 is the naive expectation that the size of the city you live in has no influence on your probability of catching the disease. And I think this is really neat. The data is perfectly consistent with theoretical expectation given by urban scaling laws prior to the invention of a diphtheria vaccine, and completely inconsistent after. I could tell you all about all the statistical tests that I ran. It holds up to a rigorous statistical analysis as well. I also sort of ran a bunch of different ways of checking for biases in the data. The results are qualitatively consistent, no matter which kinds of statistical tests and how you slice our data. All of the approaches yield the same ultimate conclusion that there's a meaningful change in the estimate of the relationship here. Okay. So that's urban scaling theory and diphtheria. This is another good point for questions if anybody would like to chime in or comment.
I wish I knew enough to ask.
I do have one question for you, Dr. Brailsford. Do we need to stop sharing the slides for folks, or I should be able to see the hands raised, correct? I will scroll through and make sure I'm not missing anybody. If you have one, go ahead and hit that function. My question was back to the beginning of your presentation, though, when you talked about, isn't it interesting that we were all part of sort of the most large scale, like, behavior change? And is there any difference in thinking about sort of, I don't know how to phrase this scientifically, so I won't, asking people to do something versus not do something? you know, the difference between, okay, I have to stay at home and not do anything versus participating in something that's more active. Is there a way of thinking about that?
Yeah, so that's an interesting point. And I mean, yes, like those are different asks, right? Don't do this is a sort of an ask to stop doing something is different than an ask to than an affirmative ask, an ask to do something new. And it's also true that our COVID mitigation in the end took many forms, right? Like some of it was stay home.
Sure.
Some of it was wear a mask. Some of it was get vaccinated. Some of it was upgrade your buildings air quality systems if you're a person who's in charge of buildings. So in the ways that I've been thinking about COVID mitigation, I sort of, in a world with perfect data, which I'm not in, I've been sort of thinking about the whole portfolio of things that we did, from stay home, closing businesses, wearing masks, social distancing, building ventilation systems, that whole portfolio of things as sort of lumped together as one mitigation action, from individual, neighborhood, community, institutional, national.
Thank you.
Mm-hmm. Yeah.
Anybody else before she moves on? If not, that's okay. I'm just scrolling through. All right, I don't think so.
All right, great. Yeah, so this little chunk of the talk is about COVID, so we get to talk more about COVID. Yay.
No, I'm fine. I'm fine.
And if folks could please mute yourselves. Thank you.
Yeah, so the COVID bit of this paper, again, emphasizes that the behavior change we experienced are the most dramatic collective behavior changes in the history of the world. Since March 2020, billions of people worldwide upended their lives in order to fight this virus with the first tool we had, which was distance. So this is one way of quantifying just how dramatic that behavior change was. Each little box here is a United States county. And so we've got typical travel behavior for each US county by day, starting in early March, where dark green is more travel and light green is less. And so we can see early on mobility, this is sort of in the normal phase of life. And then on March 12th, every national sports league closed. And over the next 2 weeks, mobility fell to just 10% of normal levels. We remember this, right? This is when everybody was baking bread. Mobility remained quite low through the end of March into mid-April. And starting in mid-April, we started to see the safer at home policies come into effect. And then at the same time, mobility started to recover. Those safer at home policies started to fade or age out in May and June. And then by June, typical mobility was really about half the pre-pandemic normal. We can look at this in terms of just sort of overall movement, but we can also look in terms of the places that people visited. So here we've got an index of how unusual our behavior about going places has been. The left panel shows visits to bars, the right panel shows visits to school, where dark red is very unusual drops in visits and dark blue are very unusual increases. If you want the statistical definition, it's the standard deviation in visits in a particular week compared to the full 2019 distribution. So this particular slide is showing the week that covers New Year's Eve 2019. Bar visits are up, everybody's partying, school visits are down, all the kids are on winter break, right? And here we can watch the weeks click by in early 2020. There's a handful of bad weather events in January and February, and then watch schools in New Orleans. The first week you see Mardi Gras, then Texas spring break, and now COVID's here, and the entire United States turns red. School visits stayed 2 to 7 standard deviations below typical through the summer. And then they start to sort of tentatively rebound in the United States, South and Midwest, really starting in August. Like you can start to see school visits coming back up here. Yeah, and now we're back to January. So you'd think, right, we know that it's a biological fact that if you're not interacting with a person, you can't. If you're not in the same space sharing air with a person, you almost can't catch COVID from them. reducing your mobility, reducing your interactions with other people is going to reduce your exposure and therefore the probability that you catch a disease. This is a figure then that shows logged known cases per person against an index of mobility in the Northeast for July to September 2020, where each dot is a United States county. Based on a model of the biological system alone, right, exposure is necessary for disease spread. So there ought to be a positive association between mobility and cases. This line ought to go up, not down. But no amount of statistics is going to make that relationship positive, right? And so this figure is one place in one time, blah, blah, blah. I can test it for all of the United States regions. I can test it for individual states or cities or whatever. And so each of these little colored dots then represents one analysis of sort of a whole pile of little dots here. For each of the sort of 4 major COVID waves in between March 2020 and 2021. And yes, there's really, really wide heterogeneity in the results. And the relationship got noisier as time dragged on. But 12 of these 16 time periods have a statistically significant negative association between mobility and cases, when we ought to see positive if we were only looking at the biology. So what's going on here? People, right? People make choices. And these choices are informed by our dynamic understanding of the system that we live in. So you might possibly be thinking, Krista, that's what we have epidemiologists for. They have really good models, and maybe it's something about the spread dynamics here. So maybe COVID hit cities first, and maybe that matters. SAR models are the workhorse of mathematical epidemiology. They are a really, really good tool. There's also sort of advanced statistical techniques that have been applied. But fundamentally, the core mechanisms that we have for understanding disease spread in populations say that people start out as susceptible, somebody gets infectious, that infectious person spreads their disease to other people. Eventually, some of these people, hopefully they recover, some people pass away. And the disease spreads through a population in this way. People can only go more or less, you can add fancier models, but fundamentally people go from susceptible to infectious to removed. And that whole population, and everybody fits into one of those categories. So in this worldview of using mathematics to describe how disease spreads through a population, the susceptible population only gets smaller. And we can write out the equations, right? If we want to. But a point that I think is important to note is that if you're using a mathematical model of this kind, you can there are fancier versions, right? Like I've picked the simplest one just to make it a little easier to digest and to talk. But fundamentally, all of the information about the biological characteristics of the disease and how we choose to mitigate it is squashed into this little b, into just that one little parameter. And I think that's not sufficient for cases like COVID-19, when the biology was complex and important, and so was our behavior, right? Like people did a lot of different things at large scales. So instead of focusing on unmitigated disease spread, I propose to try to model the interactions between behavior and disease. So there's a model from mathematical ecology called the Lotka-Volterra model, and it was invented to describe interactions between predators and prey. So lynxes and hares, foxes and bunnies, where if you have a bunny population and there's no predators, then the bunny population will explode, right? But if there's predators, then some of the predators will eat the bunnies, and if the predators have a lot of food, then the predator population will also grow, and eventually your bunny population will rise and your fox population will rise. And eventually there will be enough foxes eating the bunnies that the bunny population starts to fall, and then the predator population will also fall because their food source is gone, right? So you get these characteristic waves in the dynamics of predator-prey populations, right? So that actually isn't a terrible way of thinking about interactions between our mitigation behavior overall and the virus. So in this version of the world, I cast mitigation, our masks and our clean ventilation systems and our washing hands and all of those things all together. Those are the predator and the virus is the prey. To write that down in mathematical form, it looks like this. And so you get waves in cases and you get waves in mitigation. And hey, we've lived through COVID for quite a few years now. We have a lot of waves in cases. We've seen waves at the national scale. We've seen waves regionally. Right? Now, unlike the base Lotka-Volterra model, where the waves all sort of stay the same size, in our experience of COVID, these waves kept getting bigger. And that's still empirically true 4 years later. We're all also really deeply aware now of the concept of pandemic fatigue, right? Like all of us are more or less over worrying about COVID-19, or at a population level at least. COVID-19 is still here, it's still real. And many people, for legitimate reasons, are still being careful. So we can incorporate pandemic fatigue into this little model, right? You can change this parameter, its name is eta, you can let it decline with time. And what that means in human speak is that changes in mitigation effort get less sensitive to changes in risk. If there's more cases, you still have an increased response, but it's not as strong. If there's declines in cases, you have a decreased response, but again, it's not as strong. An example of this might be that if someone upgrades their ventilation system at home or at work or at school or wherever, they're not going to turn that off just because COVID is lower right now. You could also let gamma, that's this one, increase with time. And the interpretation for that is that mitigation effort declines more quickly. We're all sick of staying home. So at the first sign of good news, we might start finding the interactions that we want and need. The kids are back at school. We're getting that delayed healthcare. We're socializing because we're humans and we need that. So either of these minor changes to these two particular parameters reproduces the qualitative behavior we see in the United States experience. And this is just one strategy for modeling the temporal dynamics of coupled viral and behavioral processes. I think the important part, I think, is that it's trying to create a quantitative way of bringing humans into the disease system as a part of the system that has equal influence on the outcomes. And so I think because I think that's what we've experienced, right? Like, I think it highlights the importance of treating human processes, anthropogenic processes, as an inherent part of almost all of the systems that we care about. This is another good spot for questions if anybody's got any thoughts or comments. Okay. And the next chunk of the talk is a big brain shift. We're going from humans and disease to describing infrastructure systems. So describing inequality in access to roads and buildings, clean water, things like that, right? So so don't be too confused when I've stopped talking about disease entirely and started talking about buildings. Now, I think that theoretical strategies like urban scaling and this Lotka-Volterra model, they're cool, right? It's neat to have such a simple way to describe expectations of a variety of characteristics of systems with people in them. But those are also they are also simplified, right? In some ways, they miss characterizing true interdependencies because they don't pay attention to the heterogeneity and inequality of people's experience. But we know that urban heterogeneity, urban inequality, is a fundamental property of cities. There has never been a city in the history of humanity that doesn't have inequality. There's a lot of aspects of this, right? You can have heterogeneity in income, you can have heterogeneity in access to services, you can have heterogeneity in race, ethnicity, culture, businesses, professions. This heterogeneity makes data collection and interpretation more difficult. It's also, I think, a really useful way to start to promote faster and more effective sustainable development solutions. Because if you find because you can learn from different places within a city. So in a pair of papers in this little talk, I described the mathematical language that we're using to characterize heterogeneity and inequality in urban infrastructure, using examples from Brazil, South Africa, and India. This is a figure of population density in Brazil, using Brazil's national census from 2010. There's obviously really extreme heterogeneity here. If you look at this, if you look at this without your figure without your glasses on, you'd say, oh, nobody lives in Brazil, right? It's all green. There's no population anywhere. You kind of have to zoom in to the coasts to see that, oh, all of Brazil's people live on the coasts in these sort of super high population density areas. So the average plot of land in Brazil has a very low population density, fewer than 50 people per square kilometer. But the average person in Brazil experiences a very high population density because they live in these cities. On average, right, they can be expected to live in one of Brazil's major cities. So this is now we can zoom into the cities, right? Here's where all the people are. You get the same result in South Africa. This is data drawn from the 2001 national census. And again, South Africa's population also, in large part, lives in urban environments. You can also from this see that within a city, there's still a great deal of heterogeneity and just population density. And so now I'm going to sort of switch my lens to thinking about access to infrastructure instead of population density. So one of the reasons that this is important is that people who live in slums and informal settlements really do cite infrastructure as one of their central development concerns. Infrastructure access is a core part of meeting the UN Sustainable Development Goals and meeting the needs that have been articulated by people who live in slums and informal settlements. So this pie chart here was extracted from neighborhood surveys of populations conducted between 2014 and 2015 by an organization called Slum and Shack Dweller International, an organization that was formed in India to take census-style data of people who live in slums and informal settlements, where at the time when this organization came up, India wasn't even trying to count people who lived in informal settlements. So these surveys are one of the rare pieces of information that actually does directly express the preferences of people who live in slums and informal settlements. So we can use that information. We can create something like a sustainable development index modeled after what the UN defines as a slum, that looks at an average, a multiplicative average of access to important characteristics of living in a city: electricity, sanitation, clean water, housing quality. We didn't have data on income or education for this particular index, so the index we used is just water, electricity, sanitation, and permanent homes. So we can then measure that in all of the neighborhoods, in all of the places, right? There's significant heterogeneity in access to services within cities, and it's even partially masked at the national scale by differences between urban and rural populations. We see the same feature in a cross-scale analysis of income inequality, and then we can describe one pretty simple way of measuring inequality. So we think about geography in a nested way, right? Like the United States is the US is made up of states. States are made up of counties. Cities are made up of neighborhoods, right? You can go from a neighborhood to a city to a state to a nation. This measure of inequality relies on that idea of nested geography, that for any given level of access to infrastructure, there's a limit in how unequal things can be. Either all the people who have no infrastructure access are lumped in one place, or all the people who have all the good things are lumped in one place, or it's sort of more mixed up, right? So we can write down what the maximum inequality is, conditional on your measure of your average level of access to services. So to sort of put that on a figure, if your variance is close to zero, then your distribution of infrastructure, housing, sanitation, water, is about as equal as it could be. Or if it's up on this line here, it's about as unequal as it could be, even if nobody has anything or everybody has everything. Because our measure of infrastructure is bounded between 0 and 1, that's why we have this maximum value. So sort of with color, the darker blue would be things that are as equal as possible, where the brighter yellow is as unequal as possible, conditional on, say, half of the population having access to improved sanitation. And we can measure that for South Africa or for Brazil. And we can see that sort of what we observe in the real world is somewhere in the middle. And so this is sort of one way of characterizing a relationship between infrastructure access and the spatial heterogeneity within that city in terms of infrastructure access. And then a student of mine built on that work the invention of a way to describe inequality within a city for his dissertation at Yale. And so in this figure, Bartendu calculated the average inequality in infrastructure access in South Africa and Indian municipal regions based on that same measure. We're here, lighter colors are showing low inequality and darker colors are showing high inequality. And once you have measures of inequality, right, like we can look at it and we can slice it a bunch of different ways. What's the difference between urban and rural inequality? What's the difference between South Africa and Indian inequality? Is there a relationship between population and inequality? And so these are sort of ways that we can start to finally mathematically characterize inequality. And when we can characterize it, we can start to have a richer conversation about how we can address these challenges or use this information to solve problems in urban environments. We've also applied that to measuring inequality in pavement across cities in the United States as sort of a first step in a project I'm working on in Southeast Texas. But overall, one of the things that we've sort of started to understand is that cities really are the global place where both climate and earth system and epidemiological problems are focused. And they're also where the solutions come up from, because they concentrate all of these interdependencies across lots of different kinds of systems. Their most fundamental characteristic is interpersonal interactions. And we can finally start to measure those at scale. And then infrastructure inequality is a major characteristic of urbanization. So I think that if we can start to sort of get towards a combined understanding of all these systems building up from how we understand interactions between people and their outcomes, we can really start to solve problems. So there are generalizable patterns in the signatures of human processes at individual scales, at city scales, and at national scales. And I think that if we can understand and communicate these patterns, that's what we need to start to address the global scale problems that we see with diseases, climate change, all of these other things. I'm a DOE scientist, so my time on all of this work was funded by the National Virtual Biotechnology Laboratory, which was a federal response to the COVID Act. And then I've also been really generously funded by Oak Ridge National Laboratory through a couple of different fellowships and grants and projects. Thank you.
Thank you so much, Dr. Brailsford. If you wouldn't mind, stop sharing your screen so I can see everybody. Now is what everyone's digesting. All this thinking. Now's the time for questions. If you can use the raise hand function, I'll call on you. All right, Randy Frost.
Thank you for your presentation and all these systems you're looking at, and particularly the COVID response. I'm just wondering, family systems theory looks a lot at emotional systems, not only the individual, but the collective. and that there are patterns in emotional functioning that we can identify in families, but also extend to larger units. You mentioned that early on, and I was a few minutes late arriving, that fear was a factor in driving motivation. And I'm just wondering, you know, well and good to have the systems, but what actually interacts with human behavior to produce a predictable outcome? And it seems to me that that tension, anxiety, fear is one of those variables. And I know that people are advocating for mitigation and changes in behavior to slow down climate change. Don't want to frighten people um, or portray the situation as hopeless. But how do you think about emotion as a driver of behavior?
That's thank you for your question, Randy. This is such an interesting topic. I'm gonna answer kind of two hats, one with my scientist hat, right? And another as a person who lives in the world.
Mhm.
Scientists don't have good ways of measuring emotion, right? Not particularly good in individuals, and absolutely terrible at scale, like beyond individuals, to think about emotion in the context of collective groups of individuals. We don't have tools to measure that.
Mhm.
And a lot of the history of science has said that if we can't measure it, we can't understand. If we can't quantify it, we can't understand it, and it's not worth even studying. I disagree with that.
Mhm.
But that is the objective reality of how science has been done for centuries, right? That the social sciences, in part because they have not been quantified to the extent that, say, the natural sciences are. There hasn't been as much investment, there hasn't been as much effort, there hasn't been as much research. So scientists don't have a lot to say about emotion in these contexts. As a human who lives in the world and experiences emotion just like everyone else, I think that you're not wrong, right? Like, we do know some things about the role of emotion in individual and collective responses. Rebecca Solnit writes, at great length about the importance of treating climate not from a doomsday perspective, but from a problem that we have access to solutions for, because the qualitative literature about human behavior suggests that when we see a viable path forward, we're more likely to act. And that action then creates a better pathway, right? So, we don't have large scale empirical evidence. We cannot run emotional experiments on cities. We never ought to be able to. But extrapolating from what we know about individuals suggests that that's a logical approach.
Mhm. I was just thinking with COVID, such a dramatic behavioral response in such a short period of time. I mean, people were afraid, and they had reason to be, and that I would think had a lot to do with the rapid response you can pick up with the statistics and studies. But the problem with climate change is it's not so evident that it's immediate or even short term. And so the human sort of puts that off because it's not an immediate threat.
Mhm.
And so I'm just thinking that maybe there's a place for mobilizing political will out of fear and out of effective political rhetoric among people competing for office who make decisions about what we're going to do or not do. Um, what if a politician said to somebody in Texas, in the middle of the summer, hot enough for you? Well, keep voting for your congressman who is standing in the way of passing legislation to reduce the effects of climate change. in other words, if emotion is more a driver of human behavior than rational statistics, logic, and facts, even, maybe we ought to pay more attention to mobilizing emotion uh, to promote change.
I mean, we do know that statistics and facts in the world that I live in are not effective tools for behavior change, right? Like, I know that. I'm a nerd. I like numbers. Some
Yeah,
people's eyes glaze over. I would argue that 40 years of climate scientists articulating a legitimate concern about the future of life on Earth hasn't also, that sort of fear-based messaging that climate scientists have intuitively used to try to articulate the extent to which climate change is a crisis for humanity, hasn't made much influence in people's behavior. The kinds of things so far that it seems like have an influence are not fear, not statistics, but optimism and opportunity.
Okay. Good. Well, how would you say, if you look at a trajectory of change that needs to occur for the climate not to get out of hand for the human, how are we doing? Are we on track?
We're the sort of early evidence from the IPCC and the National Climate Assessment is that we are kind of in the middle, that we appear to not be on the worst case trajectories. We're not on the best case trajectories either, but we're not on the worst case. The future is up to us.
Okay. All right. Well, thank you. I just am interested in the interrelation of principle and fact and emotion, and wondering if we have the mix right yet. And putting out the facts should give people pause, but it doesn't seem to have as much as needs to occur.
Facts aren't very convincing in getting people to change their behaviors.
Yeah.
Right. Thank you, Randy.
Sure.
Ellen McRae.
I was thinking about Dr. Smith, your thing about, is there a difference between people being given information about what to do versus information about what not to do? And just from a personal perspective, I think with COVID, there was lots of here's what to do, lots of instruction, although that was often changing, especially in the beginning. But it was I experienced it as very active about what to do. And then with climate change, it feels like a lot, at least to me, feels like a lot of don't do this, don't do that. But I'm never quite sure what I can do to impact, especially as an individual, other than vote. But I only get one vote, and the votes don't seem to go the way I vote. But so I experienced just a pretty big difference in the way the COVID stuff went, in terms of feeling like I could have an impact or do something. So I don't know. That's just an emotional thought, feeling.
Yeah, I mean, our experience of, in some ways, COVID-19 and the climate crisis are the same in that they're a global scale problem that requires global scale collective action to address, right? And in some ways they're very different, because climate change is unfolding on the time scale of decades to centuries, and COVID unfolded, in days and weeks. And so, all of us theoretically could say, if we need to reduce our carbon emissions by 80% next week, we could do that. Like, we could theoretically live for a week with our lights off and drive less and not take our trips, right? Like, that's kind of what we did for COVID. But we also at the same time know that a week of non-energy use isn't sustainable on the timescale at which climate change is a problem. And the consequences of climate change are much less direct than catching a scary unknown disease that you might die from tomorrow, right? So you're right that there are some similarities and there's also dramatic differences. And I don't know how we get towards a coherent, actionable list of things that you can do that will have a realistic chance at solving climate change. Rebecca Solnit, who I've cited before, really is one of my favorite thinkers on addressing the climate crisis. She published a book now, it's about a year ago, that's called something like Turning the Climate Crisis from Despair to Opportunity, or something like that. Where she articulates a whole slew of things that people and individuals have done that do have a real and a meaningful impact, that some of the story that we all believe, and that in some ways even I'm telling you that we've done nothing for climate so far, is not true, right? Like, there are a lot of things that have been done in the background that are in some ways invisible, or are still nascent, that are having a big effect on the climate. And I'm guilty myself of not highlighting those stories enough.
Thank you.
There's
Anybody
also,
else? Oh, sorry, go ahead.
yeah.
Dr. Chris.
I got one question in the chat. Barbara wondered, I'm interested in the measures for interpersonal interactions. How do they get captured in real time? Can they be tagged to family members or friend categories? The data that we have on interpersonal interactions is still much less rich than the data that we experience. The data that we have as scientists on interpersonal interactions is still much less rich than the data that we all experience as humans who live in the world and interact with people, right? So some of the classes of data that we get are from cell phone, like it's never universal, it's never everybody, but sometimes some cell phone companies will release data sets about anonymized numbers that make phone calls to other anonymized numbers, and we can use that as a measure of interpersonal interactions. Sometimes those are also tagged to it or combined with a tiny bit of sociodemographic data, not usually sort of family or friend, but male or female, or broad job classification categories. Sometimes some of this data comes out of corporation email logs. The Enron corpus was a set of emails from Enron when they failed that was released, I think, because of the legal stuff, but it's become a really important set of information that social scientists use to look at interactions. There's some anonymized data from Facebook and the social media stuff that can also be used.
All right, Dixie, you're up.
Hi, I was, well, here's where my thinking went. I've lived in all of the prairie provinces in Canada. That's the only place I've ever lived. From a city of 200,000 was the biggest, down to 200, and now I'm in a little town that's 2,000 people. And so I was thinking at the beginning, you had some stats on urban versus rural, and certainly in Canada, there is more, the cities vote more left wing. And if you want to look at left wing as more as a collective focus versus right wing, at least in Canada, I've noticed that difference between sort of political views, urban and rural. I would say I'm a bit of an outlier. So obviously it's, there's people who think differently. But I was thinking, our family went to New Zealand in 2018, and it just struck me, being on this southern coastal town, I'm like, this is why rising oceans, could be problematic. Whereas my little prairie town, it's never on the radar. So I'm just wondering what your thoughts are on rural versus urban. I don't know, in so many different ways, in thought and in functioning. Does that make sense?
Yeah, it does. Right. And the pattern that you've noticed has been well observed in the scientific literature. I work for the Department of Energy, so I try to stay pretty far away from anything that uses political labels. But the sort of urban scaling theory, this idea that I referenced, that there's a systematic relationship between city size and a whole slew of things, right? Wealth, crime, disease, innovation, patenting. The underlying idea behind that is that interactions between people happen at higher rates in cities because cities have more dense populations. And when you interact with a lot of different people, that leads to different kinds of outcomes. Because people's experiences are different, not because the people are different.
All right, Dr. Pepper.
Yes, thank you. Thank you for the talk. I thought it was quite marvelous. It made me wish I knew much more about mathematics and statistics. But if I understood you correctly, you're making a very strong case for including the human as an endogenous element in the system of the development and process of these diseases or whatever else you're doing. And that makes a great deal of sense to me. My question to you is more of a general one. It's, if you were to sit down with a United States senator, what would you say to him or her about the relevance of what you're studying to the policies he or she is going to create for the future?
Mm-hmm. So thank you for your question. That's an interesting one. As a scientist at a government laboratory, one of the lines that we get told from absolutely day one is that we do not recommend policy, right? Like, our job is not to suggest policy or anything. It's to provide information that other people might think is policy relevant, that other people might use to make better policies. I think so sort of in terms of the research that can produce the information that's useful that might come up with here's a kind of solution. When we have climate research that's at decision relevant scales, right? Like climate research as, I'm sorry, I missed your name. But the woman earlier who was saying, what do I do about climate change, right? Like, if we want to do the science that can give good, rigorous, quantitative answers to what can individuals do, what can cities do, what can corporations do, we need climate science at a fine scale. We need climate science at the scale of cities, where it might be, we have really, we turn all of our really excellent machinery that's been used to study the world towards studying one project I'm working on, flood inundation in Beaumont, Texas, right? Like, the people in Beaumont, it's not relevant exactly how much sea level rise we're going to have over the next century. What's relevant is where in Beaumont is at risk. And people in Beaumont can make decisions about their exposure to risk when they have good quality quantitative information about the risks that they experience in their particular location. I think that if we had, the little models that I have, the Lutka-Volterra model, or the average urban scaling theories like that about the statistical properties of collections of human beings. If we had more of those, I think they'd be useful for creating better policies. If we lived in a world where policy was scientifically driven.
I hear that. It's a really interesting challenge. Is your field, it seemed to me as I was listening to you, and I heard you, that you work for a government agency and you're just collecting data and knowledge, you're not representing policies. But do people in your field, are you communicating with social psychologists, for example, who know a great deal about structuring processes to motivate human behavior, or to the collective behavioral people, say Ian Cousin, for example, and Max Planck. Is there a correspondence going on among these various disciplines?
Teeny bit. I in many
That's
ways,
what I was afraid you were going to say.
in many ways, I've dedicated my career towards building that bridge, and it hasn't been easy in the space that I work in.
I bet.
There are other, there's other institutions and universities where that's easier, but there needs to be more of it.
Okay, well, thanks very much.
Andrea?
I appreciated your talk as, an abstract look at change. It was very dramatic, I thought. So it made me think about and wonder about how do you reinforce positive interactions, like in the water example, the bottom of the hierarchy people get less, like Flint, Michigan, be a good example that their water supply is tainted and nobody does anything because they're not that influential. And I studied the work of a rat scientist, Jack Calhoun, who Dr. Papro also looks at. And what he suggested is that humans can't really, like mice, they can't really change that much. It's all about reinforcement of behavior. And what he did is he forced these mice to cooperate. And two mice had to go down, they had to recognize each other as individuals, go down and press a bar, and then water would come out to reward each of them. And these mice could stand something like 8 times the density that the other untrained for cooperation mice could do. And I was just thinking about if he had met you, and you guys were talking to each other about reinforcing, in other words, cooperation over fear, something like that. And I don't know if that makes any sense to you, but to me, I came away from looking at all this with the idea that, we're not going to reason our way out of this. And we're not going to fear our way out of it either. There's been plenty of fear and people are still not motivated. So I'm just still wondering, how do you motivate people toward corrective behavior? So you give your information to somebody or another and they look at it and say, look, I've got some interesting information, we should change. and yet I don't know if you get any feedback from what you're doing that says this is ridiculous. You can't motivate people by fear to do the right thing.
Yeah, the limited evidence that we do have, where it's maybe in the last 5 to 10 years or so that the sort of space and climate community has been willing to interact with the kinds of scientists who are skilled at interacting with groups of people. You might have gathered from my talk that I maybe don't have the best social skills. I'm really good at math, and those don't always match. Right, and so we do need collaborations, right? Like the folks who are good at running a global climate model aren't the people who should be running your community engagement meetings. And sort of creating a scientific infrastructure that allows us to talk with each other and learn hasn't been easy. But the information, the limited insights that we do have from the sort of little stuff that's been done at that scale is emphasizing exactly your point, right? That like cooperation makes people feel better, and it solves problems at different scales than just individuals working alone can. So one of a sort of a different talk I've given relying on work from a different colleague of mine. His name is Andrew Birtle. He studied fish, guppies, for his PhD, and he found that just guppies, when they you put a bunch of them in a tank and you wave a scary puppet over the guppies so that the guppies are like trying to hide in their tanks from the scary puppets. When there's one guppy in the tank, it takes so long to find the hiding spots, but the more guppies are in the tank, the more efficient they are at solving their particular problem, because they have more information to work with. And this colleague Andrew showed that qualitatively, he gets the same result with guppies and with gorillas and with caribou in the Arctic. He's had a delightful time traveling all over the world, characterizing the influence of cooperation and our ability to solve collective problems. Andrew is an animals person, not a humans person, but his work and work like his really does suggest that sort of cooperative behavior is one of the most critical solutions we have for solving problems that individuals can't solve alone.
Thank you. And I think Calhoun called it redesigning evolution. That, you know, unless you really can think about what outcome you want and then set up reinforcing parameters, it's very hard that the human thinks for themselves to be cooperative. Thank you very much. It's good.
Anyone else have a thought or question? Lori Smith.
Hi, I'm with Lori Smith. My name's Cynthia Standish. I'm a nurse, actually. And Lori invited me to hear this. And Dr. Brailsford, I was very inspired listening to your work. And I love that you're like the little bridge, because I think it's in the collaboration with interdisciplines, as this group was getting at as well, that we can find the motivation which comes to me not out of fear. Fear can motivate people, but I also think that a real experience with kind of the combination of your science and my experience of life, how my life may improve because of an understanding of a health problem or a an impact of climate change on my life or, my family's life. These kinds of things where we can go, this really makes a difference. And it kind of change in that way moves us not into the hierarchical model, but into our own experience where we're more in a shared community. So I just wanted to say, I think your work is brilliant. I'm so glad to be here tonight. And I'm really gratified. I did take pictures of your slide. I hope to share them with my daughter, who is very passionate about biodiversity. And I loved, just some of the things that you were researching. It's very helpful. Thank you so much.
Thank you. Thank you. That's really thoughtful of you to say.
All right, Priscilla Friesen.
Yes, thank you. I was thinking about the speed of which science developed vaccines. And I'm wondering what your thought is about, you're talking a little bit about science being a solution, or, what the place is for science in the solution, whatever that means. So I'm wondering what your thoughts are about how science worked related to the vaccine.
Yeah, so I'm not an expert in vaccine development. I do know that the basic theory and implementation of mRNA vaccines, has been that history is, I don't know, depending on when you say it started, a couple to a decade old, right? And that within, I think it was like 3 weeks of first sequencing the COVID-19 genome, we had the functional form of the Pfizer and the Moderna mRNA vaccines created. And so that whole year-long wait was functionally testing. But the reason that we could create the specific vaccine that we needed in a couple of weeks was because we had this long history of science and advanced scientists, saying, I think mRNA vaccines are maybe a useful strategy. Like, I'm going to try it for a while. And then there was the H1N1 pandemic in 2009 that also sort of spurred a lot of investment in vaccines, which really did help us out. And in some ways, when I'm feeling grand about the work that I do, when I think maybe I have a chance to make a difference, I feel like the sort of long-term view I have about the questions that are important of sort of We need to develop the mathematical language to understand people as part of the physical and natural systems that we're already good at modeling. When we have that language, then we can come up with tools that are useful for problem solving. That's the grand version of if my science is useful for society, that's what it does.
And it sounds like having a pandemic every once in a while might help expedite science.
It changes it. I don't want to vote for any more pandemics, but it does change the landscape.
Thank you.
Anybody else? Got a little bit of time left. All right. Well, if not, I think we can wrap things up early. Thank you so much, Dr. Brailsford, for your thinking and for your enthusiasm. I think it was much appreciated this evening. And my apologies for getting your location wrong at the beginning. My husband was actually getting to go to Los Alamos for the first time this week, and it was like going to Disney World for him. So he was very excited. So thank you so much for taking your time to be with us tonight. And I just want to direct folks to the chat box. You see the information about the clinical conference with Bob Noon that we're having tomorrow, if you're interested in that. And otherwise, for the professional lecture series, I'll see you all on February 15th when Dr. Barbara Lehman is going to be talking about some of her work. So I hope to see you there.
Thank you, everyone.
Good night.
Bye.